Good afternoon. Here, I will read about the conversation law, force and fire. Before that, it would be better if I introduce myself first. My name is Warnisa Gulo, NPM G1D011054, Electrical Engineering Study Program, BENGKULU University. Okay, let's just read the conservation law. The most important property of electric charge is that it's conserved. This, of course, means that the total charge in a system cannot change. But it means much more than that because electric charge is conserved locally. An electric charge cannot just vanish from one part of the universe and turn up somewhere else. It can only leave one point in space by moving to a neighboring point. The property of local conservation means that ρ can change in time only if there is a compensating current flowing into or out of the region. We express this in the continuity equation. Delta ρ by delta T plus nabla times G or Joule equal 0. This is an important equation. It arises in any situation where there is some quantity that is locally conserved. To see why the continuity equation captures the right physics, it's best to consider the change in the total charge Q contained in some region V. dq by dt equal integral for V d cubic x delta ρ by delta T equal minus integral V d cubic x nabla times Joule equal minus integral for s Joule times d is. From our previous discussion, integral for s Joule times ds is the total current flowing out through the boundary S of the region V. It's the total charge flowing out rather than in because d is the outer normal to region V. The minus sign is there to ensure that if the net flow of current is ordered, then the total charge decreases. If there is not current flowing of the region, then dq by dt equal 0. This is the statement of global conservation of charge. In many applications, we will take V to be all of space r cubic, with both charge and currents localized in some compact region. This ensures that the total charge remains constant. Forces and fields. Any particle that carries electrical charge experiences the force of electromagnetism, but the force does not act directly between particles. Instead, nature chooses to introduce intermediaries. These are fields. In physics, a field is a dynamical quantity which takes a value at every point in space and time. To describe the force of electromagnetism, we need to introduce two fields, each of which is a three-dimensional vector. They are called the electrical field epsilon and magnetic field B or beta. Epsilon x t and beta x t. When we talk about a force in modern physics, we really mean an intricate interplay between particles and fields. There are two aspects to this. First, the charged particles create both electric and magnetic fields. Second, the electrical and magnetic fields guide the charged particles, telling them how to move. This motion, in turn, changes the fields that the particles create. We are left with a beautiful dance with the particles and fields as two partners, each dictating the move of the other. This dance between particles and fields provides a paradigm which all other forces in nature follow. It feels like there should be a deep reason that nature chose the introduced fields associated to all the forces. And indeed, this approach does provide one overriding advantage. All interactions are local. Any object, whether particle or field, affect things only in its immediate neighborhood. This influence can propagate through the field to reach another point in space. But it does not do so instantaneously. It takes time for a particle in one part of space to influence a particle elsewhere. This lack of instantaneous interaction allows us to introduce forces which are compatible with the theory of special relativity, something that we will explore in more detail in section 5. The purpose of this course is to provide a mathematical description of the interplay between particles and electromagnetic fields. In fact, you've already met one side of this dance. The position R T of a particle of charge Q is dictated by the electrical and magnetic fields through the Lorentz force law. F equal Q epsilon plus R times beta. The motion of the particle can then be determined through Newton's equation F equal mr. We explore various solutions to this in the dynamics and relativity course. Roughly speaking, an electric field accelerates a particle in the direction epsilon, while a magnetic field causes a particle to move in circles in the plane perpendicular to B. We can also write the Lorentz force law in terms of the charge distribution rho xt and the current density joule xt. Now, we talk in terms of the force density Fxt, which is the force acting on a small volume at point X. Now the Lorentz force law reads: F equal rho epsilon plus Rho plus beta. Until here our discussion. Thank you.